Okay, test for symmetry. There is a algebraic approach and there's a graphical approach. We're going to first look at the algebraic approach so that we can understand how a function algebraically can be symmetric, whether it has even odd symmetry or no symmetry at all. And then we can look at the graphical approach. So if we look at with the algebraic talking about symmetry, we have the point xy that's on some graph. The graph itself is symmetric to the x-axis, which means the horizontal x-axis. We flip that graph over the x-axis. Our x value does not change, but our y value becomes the opposite of what it originally was. So if we have some point, let's say I won't use my hand up in front of the camera. Let's say we have a point right here that is, we'll just call it 1, 1. If I flip it over the x-axis, it still has a positive x value of 1, but now it's negative 1 on the y-axis. And then the opposite is also true. If I started at 1, negative 1, and I flip it over the x-axis, it goes to positive 1, 1. So it's going to be, if it's symmetric with respect to the x-axis, any ordered pair is going to be x and the opposite of y. That will be our new ordered pairs for the reflection. For symmetry about the y-axis, it's just the opposite. Our xy ordered pair, y value stays the same, but we now take the opposite of the x value. And if it's symmetric with respect to the origin, which means it would be the line y equals x, we just take the opposite of both values, and we will have the new ordered pairs based on that symmetry. So there's a couple of ways to test this symmetry, and those are listed right here in this blue box. The first one, if we want to check for x-axis symmetry, we replace y with negative y in the equation. If an equivalent equation results, the graph of the equation is symmetric with respect to the x-axis. For the y-axis symmetry, we replace x with negative x. If an equivalent equation results, then it has y-axis symmetry. The origin, we replace x by negative x, and if we get and y by negative y, sorry. And if equivalent equation results, then the graph of the equation is symmetric with respect to the origin. Just read that. I'm not saying, oh, hey, you have to know every word that just came out of my mouth from that blue box, but it's going to be helpful as we go through these examples. You'll start to pick it up a little bit better. So example 5, it says test y equals 4x squared over x squared plus 1 for symmetry. So let's first test it for x-axis symmetry. I'll do the x-axis symmetry in red. So we're going to replace y with negative y. Whoops. Okay, so we're testing for x-axis symmetry. And if I look at that, this expression that I have written now, negative y equals 4x squared over x squared plus 1, is not the same as our original expression. That's pretty obvious. Sometimes there'll be simplifications that'll occur that will make this to where we'll see that it is the same expression. But in this case, we can clearly see it is not the same expression, because negative y equals 4x squared over x squared plus 1 is not the same. These two are not the same. So that means it is not symmetric with respect to the x-axis. So we can just write not symmetric. That one was pretty straightforward. The second one, we'll do it in this pinkish purple color, is we're going to check y-axis symmetry. So it says to replace x with negative x. So we're doing y-axis. So we take our x value and we replace it with negative x. And let's simplify it to see if we come up with the exact same expression. Negative x quantity squared is positive x squared, because a negative times a negative is positive. And we get the same thing in the denominator. And you notice what we ended up with, our result here, is exactly the same as the expression we started with. So this is symmetric with respect to the y-axis. All right, and our last test we will do in orange. That's the excuse me, the origin symmetry. So we're going to replace all of our values with their opposites. And so that means I replace y with negative y. I replace x with negative x. And I check to see if I come up with the same expression that I started with. If I don't, then it is not symmetric with respect to the origin. Well, we can see here that the test for origin symmetry is exactly the same as our x-axis test for symmetry. So it is not symmetric with respect to the origin. So this graph only has one kind of symmetry. It's symmetric with respect to the y-axis. And I'm not going to be a lazy turd, so I paused the video for a second there so I could go set up my calculator. And I want to illustrate this to you graphically. So we tested it algebraically. Let's graph the equation 4x squared over x squared plus 1. So when I graph this, okay, you can see the symmetry with respect to the vertical y-axis. That graph is a mirror image on either side. It's not a mirror image over the x-axis, and it's not a mirror image over the line y equals x. And I'm just going to put the line y equals x in there because that would indicate our origin symmetry. You can see that's not a mirror image over that line either. So we can see both graphically here on the screen right now that this graph has y-axis symmetry, and we can see it algebraically through our tests that it does not have x-axis or origin symmetry, but only has y-axis symmetry. The next one says to graph the equation y equals x cubed by plotting points, find any intercepts, and check for symmetry. The graph of y equals x cubed hopefully is one of those that you guys are familiar with already, but if it's not, we can come up with some points here that are going to work. So let's just take a small table of values. Let's start out at -2, -1, 0, 1, and 2. If I cube -2, I get -8. If I cube -1, I get -1, 0, 1, +8. So if I plot these points, -2, let's see, 1, 2, 3, 4, 5, 6, 7, 8. -1, 1, 0, 0, 1, 1, and then 2, 8. Well, you guys get the idea. I kind of missed my point there. But the graph of x cubed, that's one that we should know what it looks like. And if you look at this graph, it does not have y-axis symmetry because it's not a mirror image over the y-axis. It doesn't have x-axis symmetry either. What it does have is origin symmetry, and we're going to test that algebraically. We visually can see that, but if we test it algebraically, remember origin symmetry, replace x and y with their opposites. So -y equals -x quantity cubed, and we get -y equals -x cubed. Well, if I divide both sides by that -1, I get my original function. So we do have origin symmetry, and I'm going to go ahead and pull the calculator up and verify that again. So let's go ahead and graph x cubed. What happened there? X cubed. And then if I graph the line y equals x, okay, that graph ends up being a mirror image. Zoom in a little bit so we can see that maybe a little bit better. Okay, there you can kind of see that. So that graph, if we folded it over folded over the origin, you would see that it is a mirror image. So this does have origin symmetry, but it doesn't have y-axis or x-axis symmetry. And our next example, x equals y squared. Find any intercepts and check for symmetry first. X equals y squared. If we solve that for y, we get y equals the square root of x. Y equals the square root of x is another graph that we should know, and if you don't know it off the top of your head, you will get familiar with it. So it does have an x-intercept and a y-intercept at the origin. If we do a table of values, it's easy to use perfect squares, obviously. So we have 0, 4, 9, 16, and that's far enough. So the square root of 0 is 0, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. If I go across my axis right here, so I already have 0, 0. When I go out here to positive 4, I get a y value of 2. When I go out to positive 9, so let's see, there's 8, 9, I get a y value of 3. And 16 actually going to end up being off the graph. But we get this graph right here, y equals the square root of x. That graph lies completely in the first quadrant. So it does not have symmetry with respect to the x-axis, the y-axis, or the origin. And we can see that again graphically. If I graph the square root of x, there we go. All right. And there's the graph of the square root of x. And if I zoom out to the standard viewing window, there's the graph. So there's nothing below the x-axis for it to correspond to, so there we can eliminate the x-axis symmetry. There's nothing on the left-hand side of the y-axis for it to correspond to, so we can eliminate y-axis symmetry. And if we drew the line y equals x through the origin, again, it's not going to correspond to anything. There's no similarity on either side of the line, so it does not have origin symmetry. So this graph has no symmetry whatsoever. Here we have the graph of y equals 1 over x. Find any intercepts, check for symmetry. Well, we obviously know that x can't be 0 because we can't divide by 0. So what we end up with in that case is a vertical asymptote. I'm just going to sketch that in here. And we're going to talk more about asymptotes much later. But this is a boundary line that this graph will not cross. So let's, we know there's no intercepts. It's not going to cross that line. And it'll never get to 0, so it's never going to cross the x-axis. It's going to get really, really close to 0. So in your mind, think about what happens when we divide 1 by an incredibly small number. Rather than even think about an incredibly small number, let's just say if we divided 1 by 1/2, we get 2, right? If we go even smaller than 1/2, say 1/8, if we divide 1 by 1/8, we get 8. So 1 divided by a 32nd is going to be 32. So the closer our x values get to 0, the bigger our y values are getting. But now what happens when we divide it by, say, 1,000? We get 1/1000th. If we divide it by 1,000,000, we get 1/1,000,000th. So the larger our x values get, the smaller our y values get. And that's just one of those kind of intuitive things that you want to think about and you can come up with. I'm not going to create a table of values because it would be very difficult to get a good representation without using some really large and exceptionally small values to do. But is that it? We also have negative x values that we can look at. So if I divide 1 by a negative small value, negative 1/2 for example, I would get negative 2. If I divide it by negative 1/8, I would get negative 8. So what's happening on the negative side is just the opposite of what happened on the positive side. And this is actually what our graph looks like. It's called a hyperbola. And we can see that graphically again. But before I go on, just take a second, look at this. What kind of symmetry does that graph have? While you're thinking about that, I'm going to go ahead and plot the graph. Think about the symmetry. What is it? Okay, there's the graph of y equals 1 over x. If you said, and I'm sure you probably sat right there and looked at your computer and said out loud, oh, it has origin symmetry. You didn't. But I'd slice to think that you might have. It does not have y-axis symmetry because the right-hand side of the graph lies above the x-axis, the left-hand side of the graph lies below the x-axis. So it's not a mirror image over the y-axis. Again, it's not a mirror image over the x-axis because one half of the graph lies to the left of the y-axis, one half lies to the right. But if I did put the line y equals x through there, you can see that it does have origin symmetry. Put that in. There you go. So if I folded it over that line y equals x, it is going to lie on top of itself. It's a mirror image over the line y equals x. And we have found the symmetry for the graph of 1 over x. I think that was the last example. It is. We really have one more section of notes that should be kind of, some of you have already made fun of me, but we should be the baby math review, and then we'll start getting into more of the core of the college algebra class. So I hope you guys are having a great day. I have spent my snow day making videos apparently. I have no life. So I will see you in the morning.